In this example, we're going to look at the method of Lagrange multipliers for two constraints, and then we'll apply the method to example 4.3.3. So it can be useful to apply more than one constraint at a time when optimizing a function. The method of Lagrange multipliers can be adapted to this situation. When f of x, y, z has extrema subject to constraints g of x, y, z equals k, and h of x, y, z equals c, where k and c are constants, and when the gradient of g is non-zero, the gradient of h is non-zero, and the two gradients are non-parallel, the extrema of f can be found by solving a system of equations which is similar to the system that we solved for Lagrange with one constraint. This time, however, we need the gradient of f to be a linear combination. So lambda times the gradient of g plus mu times the gradient of h with the two constraint equations. Now it should be noted that there are actually 5 equations here, the two constraint equations, and one equation for each of the components of the gradients. There are also 5 unknowns, x, y, z, lambda, and mu. Once we have solved the system of equations, we will evaluate all of the points of our solution in function f, and if f has a minimum, then the smallest value that we get from step 1 will be that minimum, and if f has a maximum, the largest of those values will be that maximum. But it's worth pointing out that just as with the method for a single constraint, caution must be used when applying this method. If f has no extrema, this system may still have solutions, but they will be phantom solutions in that they'll be solutions of the system, but not solutions of, or not extrema of f if f has no extrema. Example 4.3.3. We're asked to find the maximum value of the function f of x, y, z is equal to x plus 2y plus 3z on the curve of intersection of the plane x minus y plus z equals 1 and the cylinder x squared plus y squared is equal to 1. We'll begin by looking at what this curve of intersection looks like graphically. So if we have a cylinder x squared plus y squared is equal to 1, that's a right circular cylinder. And if we have a plane like the plane x minus y plus z is equal to 1, it's going to come and cut that cylinder at a curve. The intersection of two surfaces is a curve. And the intersection of these two surfaces will be an ellipse. And so if we give a little bit of shading here, that will help see exactly the situation more clearly. So there's our plane. There's the cylinder, and the curve that I've shaded in red is the curve of intersection. It's those points, the points on that curve in red, that we want to take as the domain over which we want to maximize and, nope, just maximize f. So we want to maximize the function f of x, y, z, which is x plus 2y plus 3z, subject to the two constraints. We'll call the plane g of x, y, z is x minus y plus z, and we will take it at the level surface where g equals 1. And the cylinder h of x, y, z, which is x squared plus y squared, we'll take that at the level surface where h is equal to 1. We need some gradients to set up the system of equations for Lagrange. So let's calculate the gradients of these three functions. The gradient of f, taking the partials of this expression with respect to x, y, and z, I get a constant vector 1, 2, and 3. The gradient of g, so now the partials of this expression, we also get a constant vector 1, minus 1, and 1. And lastly, the gradient of h, 2x 2y, and since there is no z, 0. So to set up the system of equations for Lagrange, we need to take the first component of x, make it lambda times the first component of g, and mu times the first component of h. In other words, we get the equation 1 is equal to 1 times lambda plus mu times 2x. Next we get, on the y components, 2 is equal to minus lambda plus mu times 2y, and 3 is equal to lambda plus mu times 0. That's really nice. Lambda is solved for already. Now with these two, we also need the constraint equations. So let's put them into our system of equations. X minus y plus z is equal to 1, and x squared plus y squared is equal to 1. This is the system of 5 equations, 5 unknowns that we need to solve. Let's begin by taking lambda is equal to 3 and plugging it into the equations above. So I get 1 is equal to 3 plus 2 mu x, or minus 2 is 2 mu x, or x is minus 1 over mu. The next equation, 2 is equal to minus 3 plus 2 mu y, or 5 is equal to 2 mu y, or y is equal to 5 over 2 mu. We're going to take these expressions for x and y and plug them into x squared plus y squared is equal to 1. So if we do that, we're going to have minus 1 over mu squared plus 5 over 2 mu squared is equal to 1. We're going to be able to solve for mu. We get 1 over mu squared plus 25 over 4 mu squared is equal to 1. If we multiply both sides by mu squared, we're going to have 1 plus 25 over 4 is mu squared, or putting things on a common denominator, 29 over 4 is mu squared, so mu is equal to plus or minus the root of 29 over 2. Taking those mu values and putting them back into x and y, well, let's deal with them one at a time. If mu is the root of 29 over 2, then we get x is minus the reciprocal of that, so minus 2 over the root of 29. Y is going to be 5 over 2 mu, so we're going to get 5 over the square root of 29. And z we can solve for using our remaining equation. So if we take the equation of the plane and isolate z, we're going to have z is 1 minus x plus y, which is going to be root 29 plus 2 plus 5 all over root 29, or root 29 plus 7 over root 29. That was one possible value of mu. Let's look at the other one. Actually, before we do, let's call the point that we've just found A. Minus 2 over root 29 is the x coordinate. 5 over root 29 is the y coordinate, and the z coordinate we just found here is the root of 29 plus 7 over root 29. So the other value that we had for mu was minus root 29 over 2. And if we plug these into the same expressions for x and y and z, we're going to get that x is just the negative of what we had before, so 2 over root 29. y is also the negative of what we had before, minus 5 over root 29. And if we solve for z and plug in x and y as these values, we are going to have the root 29, but the signs here will switch. And so we'll have z is root 29 minus 7 over root 29. Now we need to evaluate our function f at each of these points. So let's call this point B. Root 29 and 5 over minus 5 over root 29 and root 29 minus 7 over root 29. So f at A, I've evaluated our function f, which is, don't forget, the function f of x, y, z is x plus 2y plus 3z. I've evaluated f at both of these points, and f at A gives us 3 plus root 29. F at B I've also evaluated off screen for us, and f at B gave us 3 minus root 29. This clearly is the bigger value. The question is, does f really have a maximum or not? If it does, we know we found it. So we can look back at our curve of intersection. Our curve of intersection is an ellipse which is on the surface of this cylinder. It is closed and bounded. So the extreme value theorem guarantees us that we have a maximum. So because the curve of intersection is closed and bounded, then the extreme value theorem guarantees us absolute extrema. On this set. Lagrange therefore has located them for us. So f has a maximum of 3 plus root of 29 at the point A.